A groundbreaking discovery in the depths of our oceans may just reshape our understanding of oxygen production and its environmental implications. Scientists have uncovered something extraordinary in the dark abyss of the ocean.
For 10 years, Professor Andrew Sweetman believed his deep-sea sensors were broken. Every reading from the abyss showed oxygen rising where none should exist. Then, in 2024, the impossible was confirmed. Something in total darkness is creating oxygen, a phenomenon now called dark oxygen, rewriting the story of life on Earth and exposing a hidden force that could fuel alien oceans or doom ours if we mine it away. Why did we ignore this miracle for so long, and what happens now that the secret is out? Andrew Sweetman stood on the deck of the research vessel, staring at the incoming data with a mounting sense of frustration. The oxygen readings from the abyss kept climbing, sometimes tripling in sealed chambers over 2 days. He checked the calibration logs, swapped out sensor heads, and ran diagnostics on the landers. Nothing made sense. In the deep Clarion-Clipperton zone, 4,000 meters beneath the surface, oxygen is supposed to be steadily consumed. There is no sunlight, no photosynthetic algae, only darkness and cold. Every textbook, every lecture, every prior expedition said the same. Oxygen should go down, not up. For years, Sweetman wrote off the rising numbers as glitches. He scribbled sensor error in his field notes and flagged the files for later review. The pattern never changed. Each deployment, whether in the Nori D license area or another patch of the abyssal plain, brought the same impossible story. Some days, he wondered if the problem was the landers themselves. These robotic instruments, built to survive crushing pressure and freezing temperatures, should have been reliable, but the readings kept defying logic. Colleagues offered theories, faulty optodes, microleaks in the chambers, maybe even calibration drift from the long journey down. Sweetman cycled through every possible explanation except one. He filed away the anomalies and moved on, trusting that the answer would reveal itself in time. The frustration simmered quietly, never quite fading. Each cruise returned with more data, more questions, and the same stubborn rise in oxygen. The deep ocean, it seemed, was refusing to follow the rules. Sweetman's disbelief became routine, a silent companion on every expedition. Year after year, the numbers waited in the archive, dismissed and unexplained, until the day he could ignore them no longer. Pressure from Sweetman's colleagues began to mount as the unexplained oxygen readings continued to stack up in the archive. Each new cruise returned with more data, and each review meeting seemed to circle back to the same question. What if the anomaly was real? In cramped conference rooms and late-night emails, the doubts started to shift. Some team members argued for a final systematic review of the old logs. Others suggested bringing in outside expertise or testing the sensors in new ways. Sweetman found himself drawn back to the data he had dismissed for years. The numbers stared up from spreadsheets and handwritten notebooks, refusing to fade. One afternoon, during a routine data audit, a junior researcher pointed out that the oxygen spikes appeared at every site where nodules were abundant, but never where the seafloor was bare. That detail stuck. Sweetman began to comb through deployment records, noting the correlation. He reached out to colleagues at Northwestern University, asking if they could measure the electrical properties of nodules shipped directly from the field. The idea was simple: test the rocks themselves and rule out any chance of a biological or sensor artifact. The team met to discuss a new approach. Instead of assuming error, they would treat the anomaly as a genuine phenomenon. Plans took shape for a dedicated expedition using an entirely different set of benthic landers and oxygen sensors. Every protocol would be double-checked, every calibration verified. The goal was clear: either confirm the impossible or finally put the mystery to rest. Sweetman's skepticism gave way to determination. He committed to a full-scale investigation, knowing it might upend everything he thought he knew about the deep ocean. The decision was made. The search for answers would begin in earnest, with the team prepared to follow the evidence wherever it led. The new expedition arrived in the Clarion-Clipperton zone with a single goal: settle the oxygen mystery once and for all. The team brought a fleet of benthic landers, each outfitted with redundant oxygen sensors, optodes, and microelectrodes, all freshly calibrated. Every sensor was checked against certified standards before deployment. Each chamber was sealed tight, tested for leaks, and then lowered 4,000 meters to the seafloor. In total darkness, the experiment began. Chambers were placed over nodule fields and over bare sediment as controls. The protocols left nothing to chance. Measurements were logged in triplicate, and temperature, salinity, and pressure were recorded every minute. Within hours, the sensors over nodule-rich patches began to register a slow but unmistakable rise in oxygen. The controls, chambers without nodules, showed the expected steady decline. No sunlight, no algae, no photosynthetic life. Yet inside the sealed chambers, oxygen levels climbed, sometimes doubling over 2 days. The team rotated sensors between chambers, swapped cables, and even ran blind tests to rule out operator error. The result held firm. Oxygen rose only where nodules were present and only in the dark. To be certain, the team repeated the experiment using a second set of landers, this time in a different sector of the zone. The outcome was identical. The anomaly was real. The oxygen increase was reproducible, and it tracked precisely with the presence and surface area of the polymetallic nodules. Every check and control reinforced the same conclusion. Something on the seafloor was generating oxygen in the dark, and it was not a glitch. A technician steadied a platinum probe against the rough skin of a nodule, his gloved hand barely trembling in the chilled air of the lab. The voltmeter blinked to life, and for a moment the number seemed to hover in disbelief. 0.95 volts. Not a trace of sunlight reached these rocks, only the slow, relentless push of deep-sea chemistry. Yet the reading held steady, as if the nodule itself were a tiny battery, charged by the planet's own restless metals. Sweetman leaned in, watching the display. The same voltage appeared on nodules from different corners of the Clarion-Clipperton zone, always in darkness, always at the interface where metal met seawater. The probe mapped potential differences across the nodule's surface, tracing invisible lines from manganese-rich ridges to pockets of nickel and copper. Each reading told the same story. Electrons wanted to move. The rocks were alive with stored energy, waiting for a path to flow. In clustered nodules, the voltages could add up, sometimes reaching the strength of a household AA battery, enough in theory to push electrons through seawater and split its molecules apart. For the first time, the oxygen anomaly had a physical source. The numbers on the voltmeter matched the rise in oxygen measured in the abyss. The link was undeniable. Wherever the nodules went, so did the voltage, and with it the impossible appearance of oxygen in the dark. Sweetman and his team had caught the rocks in the act, and the rules of the deep ocean would never look the same again. A single AA battery delivers about 1.5 volts, just enough to power a flashlight or a TV remote. Now imagine that same voltage, not in your hand, but scattered across the ocean floor, stored inside potato-sized rocks. That is the reality inside the Clarion-Clipperton zone, where polymetallic nodules cluster together by the thousands. Each nodule, layered with manganese, nickel, copper, and cobalt, acts like a natural electrode. When a probe touches one of these nodules, the voltmeter can read up to 0.95 volts. That is not quite enough to split water on its own, but these rocks are rarely alone. When nodules touch and form networks, their voltages add up, sometimes reaching 1.5 volts or more, matching the output of an AA battery. In a high school chemistry lab, dropping an AA battery into a glass of salty water creates a simple circuit. The battery pushes electrons through the wires, and the salt water lets ions move between the two ends. With enough voltage, the water molecules themselves are torn apart. Hydrogen bubbles rise from one end, oxygen bubbles from the other. This is electrolysis, voltage splitting water into its basic elements. On the deep sea floor, the same principle unfolds in slow motion. The nodule's metal layers create tiny voltage differences, and seawater acts as the electrolyte. When enough nodules are in contact, electrons flow across their surfaces, and water molecules at those interfaces split. Oxygen is released, not by sunlight or plants, but by the gentle, constant push of natural voltage. The more nodules in a patch, the greater the total voltage, and the more oxygen can be produced. This is why scientists call them geobatteries. They're not alive, but they store and release energy, quietly running a chemical reaction that most people only see in a classroom demonstration. The difference is scale and time. On the seafloor, this process runs day and night, year after year, with no wires, no circuit boards, just rock, metal, and the restless chemistry of the earth. A cold water tank sits on the lab bench, filled with artificial seawater chilled to just above freezing. In the center, a cluster of polymetallic nodules rests on a glass tray, their layered surfaces glinting under the fluorescent lights. Platinum electrodes clipped to the nodules at different points connect to a voltmeter and a simple circuit. The air smells faintly of salt and metal. A technician flips the switch and the voltage climbs, 1.5 volts, matching the output of a household AA battery. Nothing happens for a moment. Then, almost imperceptibly, tiny bubbles begin to form on the nodule surfaces. Hydrogen streams from one electrode, oxygen from the other, clear, unmistakable proof that water molecules are splitting apart. The setup is simple enough for a high school science fair, but the implications are real. The same process is unfolding far below, in darkness, 4,000 meters below the Pacific. No sunlight, no algae, no plants, just rock, water, and electricity. The nodules, with their layered metals, act as natural terminals. The seawater, rich in dissolved salts, completes the circuit. As electrons flow through the nodules, they coax water molecules to break apart. Hydrogen escapes in one direction, oxygen in the other. The reaction is slow, but relentless. This is oxygen born in darkness. Lab measurements show that the rate of bubble formation depends on the number and size of nodules in contact. Larger clusters generate more voltage and more bubbles. In the cold, dark tank, the oxygen accumulates steadily, just as it does in the sealed chambers on the seafloor. Each bubble rising from the nodule's surface is a direct challenge to the old rules of biology. Oxygen, it turns out, can be born in darkness, coaxed from water by the silent push of voltage inside a rock. The experiment leaves no room for doubt. Geobatteries are real, and their chemistry is powerful enough to rewrite what we thought we knew about life's most basic element. Long before plants painted the continents green, the deep ocean was already running its own experiment with oxygen. Astrobiologists point to the abyss as a window into the earliest days of Earth, a time when sunlight barely touched the planet and life had to find another way to breathe. In these ancient waters, far from any photosynthetic algae, oxygen oases may have flickered to life around clusters of metal-rich nodules. These rocks, layered with manganese, nickel, and cobalt, do not need the sun. Their chemistry alone is enough to coax oxygen from water, sparking a reaction that would have seemed impossible just a few years ago. This discovery forces a reconsideration of what makes a world habitable. If oxygen can be born in darkness, then the rules for life are far broader than anyone imagined. Moons like Europa and Enceladus, hidden beneath miles of ice and starved of sunlight, suddenly look less like barren spheres and more like potential cradles for living things. Their oceans, rich in minerals and shielded from radiation, could host geobatteries of their own, quietly splitting water and feeding unseen ecosystems in the black. On Earth, the deep sea has always been a frontier, a place where the improbable becomes real. The idea that rocks could breathe, that oxygen could emerge without a single ray of light, is both unsettling and exhilarating. It suggests that the boundary between the living and the non-living is thinner than we thought. The story of dark oxygen is not just about chemistry. It is about the possibility that life, in some form, might be waiting in the dark on worlds we have yet to explore. Mining companies have set their sights on the Clarion-Clipperton Zone, drawn by its promise of metals that power the world's electric cars and renewable energy grids. Beneath 4,000 meters of water, the seafloor holds more nickel and cobalt than all known land reserves combined. Some estimates suggest these nodules could meet global demand for decades. The pressure to harvest them grows with each new climate summit, as governments seek alternatives to rainforest destruction and traditional mining. But the rush for resources has collided with a warning from scientists who study the abyss. Sophia Tsinikli, a leading conservation scientist, calls it human arrogance to mine the very rocks that may keep deep-sea life breathing. She points to the evidence. Every nodule stripped from the seafloor is an oxygen source lost forever. These nodules take millions of years to form, yet mining machines, giant underwater harvesters, can vacuum up the top layer in a matter of hours. Once removed, the geobatteries stop working. Oxygen production shuts off instantly, and the ecosystem faces suffocation. The International Seabed Authority, responsible for regulating mining in international waters, is locked in debate. More than 30 nations now support a moratorium, demanding that commercial mining wait until the dark oxygen cycle is understood. Meanwhile, mining companies argue that deep-sea extraction is less damaging than open-pit mines on land. The first licenses for exploitation remain pending, but test machines are already rolling across the seafloor, kicking up sediment clouds and leaving bare patches behind. The choice is stark: harvest the metals needed for a green transition, or risk creating dead zones in one of Earth's last untouched frontiers. Right now, the deep sea holds a hidden engine for life, one we barely understand, and we already threaten it. As mining companies eye the Clarion-Clipperton zone, every decision risks erasing a process millions of years in the making. We have proof that Earth's rocks breathe. The real question is, will we listen before the silence is permanent? Share your thoughts below and join the conversation.